Hey y'all, it's Arwen Smalley here, and I'm sitting here on the day when we don't have any school because of snow, I guess. And I've been thinking about class, and I noticed that there were a few folks who were maybe struggling a little bit with some of the stoichiometry, remembering it. Some people, it's been a little while since the last time you did some stoichiometry, so I thought I would try out my new technology. I just got this new camera and see how the video function works, and make a little short video for you on some stoichiometry just as a little reminder. So I also have some other videos that are available on YouTube, and I'll put that link up in the Moodle for you if you want it. But I figured this would be a little fresh start, and of course, as I said, a way to try out my new technology. So let's go. Okay, so as I said in class, just a quick reminder that stoichiometry always has to do with these mole ratios. And so the mole ratios are what I've listed here in this balanced equation. We don't have a number here, but this would be a 1. So we have 1 proportion of iron reacting with 2 proportions of nitric acid to make 1 proportion of iron nitrate and also 1 of the H2. Okay, so stoichiometry is all about these relationships of ratios. And so we can have things like 1 iron to 2 HNO3, but we can also even just look at something like HNO3 by itself and recognize that we have 1 hydrogen, 1 nitrogen, and 3 oxygens. And so this also is a ratio. So in nitric acid itself, we have a 1 hydrogen to 1 nitrogen to 3 oxygen ratio. Okay, my cat just jumped on my lap, so hopefully he doesn't start talking too much in this video too. Anyway, okay. So coming back to stoichiometry, stoichiometry is just about ratios. And so when we're doing stoichiometry problems, it's always because we are given some kind of information about one of our components. Like in class yesterday, I was telling you about how much hydrogen gas or something we had. And then we are asking about what that implies about another component. So like iron or HNO3 or whatever, okay? And so because we're talking about ratios, one way to think about this is just, you know, if you were making pancakes and I said, okay, my recipe calls for 2 eggs, right? And it also calls for a bunch of other things. So maybe I also have 1 cup of milk in my recipe. So now you're going through, and the person who made the pancake says, well, I used 5 eggs. So how many cups of milk did I use? And you're going to just use this ratio here, right? Because you would say to yourself, well, each time they used 2 eggs, they used 1 cup of milk. So I could write the way to figure out the amount by writing out this ratio, that for every 2 eggs I used, I'm using 1 cup of milk. And I put eggs in the denominator here because the eggs will then cancel out, okay? And so that gets me 5/2 cups of milk, which would be 2.5 cups of milk. And that would tell us how much milk we did. And so that's exactly the same kind of thing that we're doing every time we do a stoichiometry problem here. We're just talking about the ratios. So I'm going to just throw some numbers out here, and let's go ahead and give this a try, all right? Without the gas law right now. The next one will have the gas law in it. But for right now, then we would say something like, maybe, we have 15 grams of iron and plenty of nitric acid. So this is telling us that we have excess nitric acid. We don't need to worry about how much we have. So we might ask a question like, what is the maximum yield, the maximum amount that we can get in grams of iron nitrate? Okay. So when we're doing stoichiometry problems, the first thing that we needed to remember is this is about ratios. The second thing that we need to remember is that when we're talking about ratios in chemical equations, we are always going to be looking at moles of anything. Okay? So if we are given some grams, we're going to need to be converting this into moles somehow. If we are given milliliters, we're going to be converting those into moles. So this is where we're going to look at our information, and we're going to come back to our strategy for stoichiometry problems. And so our first stoichiometry map is going to come in here, because we just said that we are looking at going from moles. And so when we're going from grams to moles, hopefully everybody remembers that we're using the molecular weight of whatever A is, and we can also do this the other way around if we need to. And of course we can also do this using volume. We can use all kinds of different things. Right now we're just going to do grams. All right. Okay, so our first job is to figure out what's the thing that we know about, which I assign to the letter A, and what's the thing that we are asking about, which I'm assigning to the letter B. Okay, so hopefully you can see that it is the iron that we are initially talking about here. So we're going to start by putting in our grams of iron. And then you should grab your periodic table and look up the molecular weight of iron. And I'm going to do that right now here. So I've got my periodic table handy, and I see that it's 55.845 grams per mole, and I know that I need to put the grams in the bottom so that the grams will cancel out. So 55.845 grams per mole. Molecular weight is the same thing as saying that 55.845 grams is what's in 1 mole. So 55.85 grams of iron is in 1 mole of iron. Great. Okay, so I've got this all set up here, and this step now will get me to moles of A, so I'm at this step here. And now I'm going to look at my mole to mole ratio, so that's what is my way of converting between moles of A and moles of B. So from my periodic table back up here, I can see that I have a 1-to-1 relationship with iron and iron nitrate. So 1 mole of iron goes in the bottom so that my moles of iron can cancel, and 1 mole of iron nitrate goes in the top so that that persists. Okay, so now we are right here. And so I'm going to need to go to grams of B, so I need that molecular weight again. Okay, so that means I need to do a little math over here on the side. So 55.845 grams per mole, that's the iron. And then if I look at this, I have NO3 parentheses 2, so it means I have 2 nitrogens, and those each have 14.007, I think. I'm doing this from memory now. Forgot to look these ones up. Excuse me. So this is 2 nitrogens because I've got those 2. And now I have 2 times 3, that's 6 oxygens, and oxygen has that mass of 15.9994 grams per mole. And I'm going to add these guys up. All right. So let's go ahead and grab your calculator. I'm just going to do that off screen. 007 plus. Okay, so check my work here, but I get 179.855 grams per mole, and I remembered that I'm using addition rules, so I'm going to keep the smallest number of decimal places in my final answer. That's 3. Okay, so now I'm going to put this number over here, and just like this other molecular weight that we had, this also converts to 179.855 grams of iron nitrate, assuming I did the math right, per 1 mole of iron nitrate. Okay, so now we're going to multiply these through. I have 15. I'm going to divide it by 55.845. And then these are all 1, so I can pretty much ignore them. And then I'm going to multiply that answer by this 179.855. So let's go ahead and do that. Okay, so the answer that I am getting, it's a little messy, sorry about that, from doing this math is 48.309, etc. And when I look back at my significant figures, I can see that I started with 3, so that's why I'm going to keep 3. And this would be my answer for what the maximum amount of iron nitrate is that I could make in this problem. So hopefully that helps you refresh on stoichiometry. As I said, I will post a link to my other YouTube videos from Gen Chem, so you can go ahead and look up more stoichiometry problems if you need to. And also, you know, if you need any of the foundational stuff that, like developing your stoichiometry a little bit more, then go ahead and check that out too. So hopefully this was helpful, and you can let me know what you think about the video and audio quality. Have a great day.